Welcome to Data Science Made Easy. I am Divya Somakumar, and in this video, we are going to learn how to build a neural network model from scratch. Now, let us begin by first importing the necessary libraries. Import NumPy as NP, import Pandas as PD, import matplotlib.pyplot as PLT, import Seaborn as SNS. Now we have to import two more libraries, that is sequential and dense, which is used to build the neural network. From TensorFlow.keras.models, import sequential. From TensorFlow.keras.layers, import dense. So these two libraries are important for making the neural network. Now we have to import our standard scalar library, our train test split library, and our PCA library. So how do we do that? From sklearn.preprocessing, import standard scalar. From sklearn.model underscore selection, import train underscore test underscore split. From sklearn dot decomposition, import PCA. So these are our basic imports which is required to make a neural network. Now let us run this. So we have successfully imported all the necessary libraries. Now we have to import our dataset. For this, I am taking the dataset on credit card fraud transactions. This dataset is available in the Kaggle website. I will also provide the link for the dataset in the description below. I will also provide the Jupyter notebook for this neural network model. Now let us import the dataset. So, as usual, the basic import creditcard.csv. Now it is getting imported over here. By the time it gets imported, we will write our statement for importing. So tf is equals to pd dot read underscore csv credit card dot csv. Now let us look at the head of our dataset. tf dot head. So our head of the dataset looks something like this. The features are not named over here because this is a confidential data. Now there are a lot of features in this. Now let us check the columns in our dataset by checking the info of the dataset. tf.info. So we have around 3000 odd rows and we have around 31 columns, and everything is a numerical column except for your class column. But over here they have converted it into numbers and given for us already. Now let us look at the descriptive statistics. tf.describe we get our descriptive statistic, we get our mean, our standard deviation, our 25 percentile, 50 percentile, 75 percentile minimum and maximum values. Now let us check if there are any missing values in our data. So how do we do that? df dot is ne dot sum. So we have a few missing values over here. Since these numbers are very insignificant, that is, it is less than 3% of our data, we will just drop these rows which have the missing values. So let's write df dot drop ne, and we'll write in place equals true so that the changes that we make over here are permanent. Now, there are around 31 features in our data. And when there are so many features, although our accuracy may increase, but our results won't be much accurate. It won't be much robust because there are so many features. Hence, we'll have to cut down on these features. In order to reduce the features, we will use a method called principal component analysis. Now, let us apply PCA onto our data. Before we apply PCA, we'll have to divide our data into X and Y. So, over here, all the V1, V2, V up to V28, these are your features. And your class that you see over here, this is your dependent variable or the target variable which we want to predict. So, we have X is equals to df dot drop. What do we have to drop? We have to drop the class column, and we also have to drop the time column, because fraudulent transactions occur any time in a day. It's not that most number of fraudulent transactions will happen in the daytime or in the night time. So the time component is not an important element over here. Now, our y variable is nothing but our class. Y is equals to df class. Now, let us perform our principal component analysis. So, first we'll create an object for principal component analysis. Let's call it PC is equals to PCA in underscore components equals, let's say we are only taking two features, and random underscore state equals 1. Now we are going to fit this PCA onto our X and Y. Now let's do it. Let's call it components equals PC dot fit. We are going to fit it on X and Y. Fit underscore transform X comma Y. Now let us write our two principal components. PC1 is equals to components, all the row and the first column. PC2 is equals to components, all the rows and the second column. So since we know that indexing starts from 0, the first column would be indexed as 0 and the second column would be indexed as 1. Now let us make a scatter plot for PC1 and PC2. How do we do that? SNS dot scatter plot PC1 comma PC2, and we will give the hue as y, that is our target variable. Now let's run this and see. So we get a graph which looks something like this. There is something amiss over here. What is it? It is that number of fraudulent transactions are way lesser than the number of correct transactions or non fraudulent transactions. Hence, our data is highly imbalanced. Hence, it is mandatory to first do and balancing of the data. We can either use undersampling or oversampling. In this, I'll be doing oversampling because it is not good on your part to reduce your data. In undersampling, you are reducing your data and then making predictions, which is not a good sign. It is better to increase your data, to oversample your data than to undersample. So, before we go on to balancing our data, we are going to use standard scaler to scale our data because before doing a neural network, we have to scale our data. It is a mandatory condition before applying neural networks. Now, let us first scale our data. How do we do that? Let's first create an object of standard scalar. Let's call it SS is equals to standard scalar. Now we are going to fit the standard scalar onto our X train and X test. So SS dot fit underscore transform X train. And remember, fit underscore transform does not have an in place equals true parameter. So the changes that you make over here won't be permanent. Hence, to make the changes permanent, you will have to reassign it onto xtrain underscore ss. Similarly, we can do for xtest. Xtest underscore ss is equals to ss dot fit underscore transform xtest. Before we use the standard scalar, we'll have to divide our data into xtrain, xtest, and ytrain, ytest. So over here, we have used the train test split. We have taken a test size of zero point 0.2 and random underscore state is equals to 1. So now we have successfully scaled our data. Now the next step is to balance our data. So let's do that. How do we do it? We write pip install imbalance. Pip install imbalance from sklearn dot oversampling import random underscore random oversampler. Random oversampler. Now let us create an object for this random oversampler. ROS is equals to random oversampler random underscore state equals 1. Now we are going to fit this random oversampler on our X train SS and Y train. X sample, comma Y sample is equals to ROS dot fit underscore resample X train underscore SS, comma Y train. Now, at the end, we have to check if we have an balanced data set. For that, we write pd dot series by sample dot value underscore counts. So value underscore counts will give you the number of unique values in by sample. Now, let us run this. Now we have 3176 fraudulent transactions, and we have 3,176 non-fraudulent transactions. So now our data set is not imbalanced, it is imbalanced over here. Now we have to make our neural network. Before we start with our neural network, we have to first know the shape of our extreme. So extreme underscore ss dot shape. So we have 3177 rows and 29 columns. Now let us begin our neural network model. So let us make a object for this neural network. Let's call it model is equals to sequential. Now we are going to add layers. Model dot add. So in this layer, this is the dense layer. We have 32 neurons. We can write the neurons according to our wish, but it should be of the term 2 raised to n. So you can have 2 neurons, you can have 4 neurons, you can have 8, 32, 64, and so on and so forth. Now, let us write the input dimensions. So the input dimensions over here is 29. So we have total 29 inputs which are going into our neural network. So we write input underscore time is equals to 29. And we will give the activation as ReLU, because ReLU is one of the most robust activation techniques. We have Sigmoid, we have tanh, leaky ReLU, but one of the most accurate, robust techniques would be the ReLU activation. So we write activation equals ReLU. Now let's add one more layer. The more the layers that you add, the more complexity you add to your problem, but at the same time, it will solve your problem much faster. Model dot add dense. We have 32 neurons in the second layer also. Activation again, I will give it as ReLU. Now let us have one more layer before the last layer. Model dot add dense 32. Activation again, we'll give it as ReLU. You can give any activation that you like. But in the final layer, since we are solving a binary class problem, that is, we have only two classes, either it is a fraudulent transaction or it is not a fraudulent transaction. So it is mandatory that you use the sigmoid activation. Now, why is it important to have an activation in the first place? Because over here, you will be having continuous data, and we are dealing with binary classes. So continuous data will not help us predict which class would turn up. Hence, we have to send our continuous data into an activation function so that we get the classes in the form of 1 or 0. Now, let us write the final layer. Model dot add ends. And remember that in the final layer, for a binary class problem, you will only have one neuron. Activation equals sigmoid. Now let us run this. Now we have to specify the loss function and we have to specify the optimizer. Over here, the loss function is nothing but your binary cross entropy or your log loss. And I'm using the optimizer as Adam optimizer because Adam is pretty robust. In Adam, we have adaptive learning rate. So when you're away from the minimum, your learning rate is very high, and when you are getting closer to your minimum, your learning rate reduces. Adam has the property of two different optimizer. You have your RMS prop and your EDA delta. So combining those together, you have your Adam, and with that you have your momentum also. So it becomes a very robust optimizer. Now let us write model.compile, model.compile optimizer equals Adam loss equals binary underscore cross underscore entropy. Now we have to fit our model onto X sample and Y sample. So let's call it trained underscore model, trained underscore model equals model dot fit X sample, Y sample, epochs. We are going to give 20 epochs. Epochs are nothing but forward and backward propagation. So epochs is equals to 20, bat underscore size is equals to 64. So here we have our X sample, Y sample, epochs and batch size. So we have successfully trained our model. So initially the loss was 0.157. Now after 20 epochs, the loss has reduced significantly to 0.00001. So we have successfully reduced our loss function. Now the next step is plotting this loss function. Plt dot plot trained underscore model dot history of the loss. So our loss function looks something like this. So it is reducing from 0.175 to 0.000. So we are successful in reducing the loss. Now we have to fit this model onto our Y-pred. So Y-pred, we are going to predict our Y. Y-pred is equals to model dot predict x test underscore ss. Now, these vibrate values will be continuous. But do we want continuous values? We only want either 0 or 1. That is, a transaction is fraudulent or it is not fraudulent. Hence, to convert all these values which we have got into 1 or 0, we are going to write a function. Let's say vibrate equals np dot where type red greater than 0.5 1 comma 0. So if the value of vibrate is 0.5, it is considered as 1, and if the value is less than 0.5, it is considered as 0. Now, the final step is to find the accuracy of this model. How accurate is this model in predicting whether a transaction is fraudulent or not? How do we do that? We are going to check the classification report. So, from sklearn.metrics import classification underscore report, print classification underscore report Why test? Why bread? We obtain a classification report which gives us an accuracy of 100% and a precision for class 0 is 1 and the precision for class 1 is 0 and a recall for class 0 is 1 and the recall for class 1 is 0, an F1 score of 1 for 0 and 0 for 1. So, in this way, we have created a neural network model for predicting whether a transaction would be fraudulent or not. I hope how to build a model using neural networks is clear for one and all. If you have any queries, you can post it in the comment section below. Thank you.